Hello and welcome. I learned that I'm giving a crash talk on CHERI, and I've been given 15 minutes. I've written 10 minutes ambitiously on the front slide. The timer is going for 15 minutes, so let's see how we do. Normally it's a 45-minute talk that runs long, but we'll see. Okay. So I guess first of all, welcome. My name is Rob Watts. I'm a professor here in the department, along with my collaborators here, Peter Sewell, Simon Moore, SRI, Peter Neumann, Brooks Davis at Capabilities Limited. For the last however many years we've been running the CHERI project, and I've been instructed to instruct you a little bit on how this works. I'm kind of hopeful that most people here, given that they're here, have learned a bit about CHERI already, and that we're going to rely on that fact. So we first, in the form of a disclaimer, tell you and thank our sponsors, especially DARPA, who sponsored the good first 10 years of the project very heavily and still continues to support us. Innovate UK, which was responsible for digital security by design, that wrapped up I guess a couple of years ago now, and then continuing support from DCIT and EPSRC, especially for our CHERI Research Center, but also I think a lot of support going into the community, which is very much appreciated. And of course, our industrial sponsors. And I guess this is a particularly nice event to welcome you to. It's the 15th anniversary of the CHERI project. I mean, strictly speaking, 15 plus, some growing number of months, but we are going to host a 15th birthday party this evening as part of the reception that I hope you guys will all be able to join. We'll have a few words of thanks. We'll have a light dinner and some birthday cake. And very pleased to see you here. You'll find there's a CHERI exhibition, if you haven't yet seen it, out in the street, which is this big open space in the front of the building. We have everything from some of the first test chips back on CHERI microcontrollers, which you can also see live at booths and things as well. Various IP products, demonstrations on FPGA, on Morello systems, and then a very large pile of PhD dissertations, which continues to grow. We've realized that we can only accept maybe 5 more PhDs, because otherwise we run out of room in the display case. So if you're working on a PhD with Simon or me, you should get it in soon so that you can get it in the display case before we run out of space. So there you are. The exhibit signs all say 30th of April. Actually, it will run. 31st March. It will actually end on 30th of April. So brief taste of sort of history and what's going on. What is CHERI? I mean, at a high level, CHERI is an architectural protection model. In this context, and I think for many people here, architecture is going to be instruction set architecture. Perhaps you'll be used to that idea. The principle here is we're going to take something called a capability system. Let me tell you about that in a moment. And we're going to mix it up with an instruction set architecture. And this is going to be implemented by the microarchitecture. So this is the pipelines and the processor and caches and memory subsystems and so on, to expose this functionality to be used by software. And this is going to enable new security behavior in software. We'll not have in this period of time a little space to talk about these things in detail. But the objectives when we set out were kind of in the following spaces. I think as always, projects pick up new objectives. So there are new ones. But we were focused on the C and C++ programming languages. When the project began 15 years ago, the memory unsafe C and C++ languages we used almost universally for TCPs. That is still true today. And we care particularly about hypervisors, operating systems, the language runtimes that underlie our managed languages, and also web browsers, which are sort of the most phenomenally complicated pieces of software that we have available to us. I think we will hand wave later, I'm sure, a bit at Chrome, which is one of our favorite pieces of software as security people. About 47 million lines of code collectively across its dependent libraries, the application, language runtimes, etc., all in C and C++ pretty much at this point. It's responsible for a critical security vulnerability every day and a half, and on average every 2 days for a memory safety vulnerability. So those are the kinds of pieces of software that we cared about when we started the project. The 2 pitches, as you may know, are fine-grained memory protection for these languages and others potentially, and with a particular interest in deterministically closing vulnerabilities. That means it's not a probabilistic thing. It's not it works 99 out of 100 times. It's always going to work. It's going to work in the presence of side channels. It's not going to suffer from information leakage. If a leakage happens, then the mechanism has to still work, and that is really important to us. And we'll sometimes divide these benefits into 2 parts. One is what we call vulnerability mitigation, which is about deterministic closing vulnerabilities, turning them back into logical bugs, if you will. What the implications of logical bugs are, obviously we're not changing that, but what we'd like to know is you're not on your path to arbitrary code execution. We also do something related to that, which is called exploit mitigation. Exploit mitigation is about interfering with the attack mechanisms that are used to achieve, for example, arbitrary code execution or other forms of data corruption or information leakage. In the former category, vulnerability mitigation, we make the strong argument the vulnerability is no longer there. Right? In exploit mitigation, what we say is, well, we have a tool set for attackers, and we've disrupted that tool set. But maybe we're not able to reason as strongly about that. We provide both of those things. Interestingly, the latter category of features supports another thing that we find interesting, one of the key original goals, which is compartmentalization. This allows you to run arbitrary code in compartments in a very fine-grained way and resist future classes of attacks. Those two ideas are that memory protection and compartmentalization are integrally linked in the design that we have. So, and sort of concluding sort of initial thoughts, right? There are multiple industrial implementations now, from prototypes like ARM's Morello core, some of the work coming out of Google, for example. You'll see some information on Google's Coral NPU and the fact that prototyping is going on for delivery of a product that contains CHERI-related, CHERI security in a machine learning accelerator, through to products from the likes of Codasip and SCI and others, which is it's an exciting moment, and it's a nice validation of these ideas. So all these things start, if you will, in kind of the 1970s of computer design. The capability system is a design pattern, and it's applied to all kinds of things, languages and operating systems and so on. We've chosen to apply these ideas to processors. We're not unique in having done that. When you go out and look at our exhibit outside, you'll see the CAP computer, which embodied many of these ideas, but in a very different way with a historic microarchitecture. But the ideas apply today and have new uses. So one of the last papers coming out of the CAP project was around using capabilities and compartmentalization to contain Trojan horses, or as we would probably think about it today, more arbitrary code execution from your attackers. And that's a key observation. And the two ideas we like particularly coming out of these designs are the principle of least privilege, which says that you minimize the privilege software runs with, you run these little boxes with as little as possible. The attacker has less access to stuff if they achieve compromise. And then another principle which we reasoned about explicitly, but was implied, I think, in a lot of these earlier designs, well, actually, interestingly, not a CAP. And that's kind of an intentional use property. When you use privileges, it's important to use the right privilege for the right thing, because misuse of privilege can also be exploited to gain access in systems and compromise data and so on. So those who do capability systems may have heard of confused deputies. That's what this is about. So, and these principles are at the heart of CHERI's design, I guess, over 50 years later. So. Our intervention is in the instruction set architecture. Here we introduce this concept of CHERI capabilities. I'm not going to show you the usual picture of a capability because we will run out of time even without that picture. This architectural primitive is going to be, as I said, implemented by the microarchitecture. There's a new data type that floats around the capability. We implement tagged memory in the memory subsystem. This differentiates capabilities from non-capabilities while allowing them to be stored side by side in memory. And then these capabilities carry metadata to protect references. Come back to that idea in a moment, but these include things like bounds and so on, but they have rules for their use. So this differentiates, for example, for those of you who know about it, a fat pointer scheme in which you just sort of constrain spatial access and so on, from a capability model in which there is a requirement to not enable escalation of privilege. And that is an important part of this story. Then we run up into the software stack. Compilers use these primitives, primarily the operating system, but also language runtimes and so on, and we can build high-level security properties, things like spatial and temporal memory safety, compartment isolation, but perhaps importantly, with compartment isolation, safe communication between the compartments, which is really essential. Often, I think, I would say this thing very cautiously, like, oh, we understand how to do isolation. Obviously we don't, because side channels. But, isolation as a concept is relatively straightforward. It's safe communication and scalable communication, fast communication between compartments, and clean, accessible communication that make CHERI a real change from, for example, MMU-based protections. So the two ways that we primarily use CHERI today are around efficient fine-grained memory protection for C and C++. Here the argument is around vulnerability mitigation. Our target is a trade-off space between compatibility and performance and disruption to source code, all these kinds of things, and security. And our aim, generally speaking, has been to achieve deterministic mitigation of about 2/3 plus or minus of memory safety vulnerabilities. Now, complicated statement, vulnerabilities change over time, our ability to find them, etc. But I think uniformly over the past 10 or so years of evaluation, we've really seen us achieving that level of mitigation. It's not that we don't in fact mitigate more than that. We often interfere with the exploits against those other classes, but the things that we would deterministically count as mitigated, the vulnerabilities, we kind of come in here and been multiple independent assessments. Generally here the argument is around what we call modest overhead. And then the second aspect is this scalable software compartmentalization. We want to put things into smaller and smaller sandboxes and scale well. And here what we're looking at is orders of magnitude performance improvement compared to existing designs, allowing us to deploy, we hope, far more compartmentalization. There's also a compatibility story that's very important to us. We want to run legacy software. So we're referring to contemporary 64-bit architectures as legacy. Some will not necessarily find that sits well with them, but we think of it that way. And we want to run these legacy 64-bit binaries alongside our rich software environment. So in the screenshot you can see here, the vast majority of operating system kernel, entire user space, runtime, file browsers, PDF viewers, etc., all running with strong memory safety and compartmentalization. But side by side, we can run some old binaries, like maybe a JVM that hasn't been updated, although JVM has been demonstrated running using Morello's features. And likewise, we have a new Chromium web browser implementation that runs with what we call strong memory safety. Another kind of success story in this space, I think, is the CHERI architecture. Was originally developed at Microsoft Research and then has now moved out to a collaboration of different companies producing products in this space. They tuned CHERI to run with microcontrollers. They were looking at small 32-bit, relatively short pipeline designs, very constrained memory. And in doing that tuning and tuning to embedded systems, they were able to really specialize their software approach in a way that allowed you to fully exploit CHERI's abilities, so fine-grained compartmentalized design, very explicit and overt use of capabilities. But also find efficiencies for things that maybe at larger core scales don't scale as well. So they've done some really nice work around temporal safety. And you can see this industrial transition into products and prototypes across, I guess, a really significant part of industry today. I hope that in the next year we will see some even more product announcements. But when you go outside, you can see SEI's first test chip back for a taped-out microcontroller design. Some of you have probably already seen some pretty exciting live demos running there. In the exhibit, if you go outside, you'll find demonstrations of CHERI at a whole bunch of scales, from these tiny microcontrollers up through Morello, which is a high-performance, superscalar, out-of-order design. You'll see in some of these things are taped-out silicon, other things are on FPGA, in fact, maybe IP products, for example, Codicip's line of CHERI-enabled application cores and microcontrollers. But really, we've been able to demonstrate these ideas at an enormous scope of software scales and hardware scales, which is important. We want a uniform model that spans all of these things. So just a couple of results to highlight on real-world software. So we did an evaluation, for apologies for those of you who've seen this before, we did an evaluation using DARPA's AIXCC. This is the AI Cyber Challenge they've been running over the last few years. We took a case study that what they do is they inject vulnerabilities in software, and they're interested in using AI to characterize and patch these vulnerabilities. But we found this very useful because they had thoughtfully generated some open source software completely full of both historic vulnerabilities that were reintroduced and new synthetic vulnerabilities that represented kind of the state of the art of this space. So we were able to run evaluation against these. This was a really nicely run experiment in some sense. They had done this work without knowing about CHERI on that team, and we had done this work without knowing about the work that they were doing. So we brought the two things together for evaluation purposes to kind of ask what would happen in this space, especially with intentionally injected vulnerabilities. Our result was quite exciting. So we mitigated what we term 114% of the vulnerabilities that they injected. We mitigated the 12 they intended to inject, and also 2 more that they added accidentally, because when you're a C and C++ programmer, memory unsafety is the natural course. And I definitely not trying to mock them anyway. They're experienced system programmers who work with vulnerable software and so on, and having talked to the team, this was not an intentional thing. And so that's a really powerful result, and it's a well-run experiment, even if it was kind of a convergence of events unexpectedly that led us to it. And this kind of empirical study is really important to us. Another result you'll be able to see if you go out and look at the exhibit is the BlastPass vulnerability. This is a zero-day vulnerability that affected the WebP library. This is Google's WebP image processing library. So for Google, this is a first-party vulnerability, and for Apple, who shipped it in iOS, this is a third-party vulnerability. This code had seen extensive fuzzing, real-world deployment, code analysis. You can look through the Git history, and you can see various fuzzing models and so on being adapted to try and find vulnerabilities. And yet this is a simplistic heap buffer overload that had persisted in that code for an extended period. This was exploited by NSO Group for use against civil rights activists in targeted attacks in the continental United States, and was discovered by a civil rights organization kind of doing an investigation of surprising things on those activists' phones. We discovered, as a result of this experiment, again, we had no idea this was coming, deterministically mitigated with a 0% line code of change to WebP in order to have it running inside of Chromium. So the demonstration you can see out there as well. So just to wrap up this super rapid coverage, I'll make the 15-minute goal, it seems, maybe not with questions. It's a really exciting time, right? We have a lot of stuff going on right now. Some of the key concepts of this research have been validated at real scale in contemporary microarchitectures, in hundreds of millions of lines of C and C++ code running on systems. We have early industrial adoption taking place, spanning startups who are taping out their own chips for microcontrollers, through to our trillion-dollar tech companies who are exploring deployment in what I would describe vertically integrated ecosystems. These tend to be places running, on the whole right now, first-party software stacks, but we hope we'll see that begin to spread into ecosystems with third-party software stacks as well. In terms of where we go, I think that is the goal. There we are. Can we get to a place where we're running with these open ecosystems? And I think that remains one of the challenges for this community is software adaptation at scale and engagement with the software deployment models, app stores, et cetera, the scalability concerns. But I think the embedded system toehold, if you will, in the space is really promising and really exciting to see. And we also have, of course, an active research community. I will come back to tell you more about that a little bit later. Right. Thank you very much.